Good afternoon. Welcome to EE 380, the Stanford Computer Systems Colloquium. Our speaker today is Peter Rakyta. He's from Budapest, Hungary, and has been studying quantum computing for a number of years. He speaks today on highly optimized quantum circuits synthesized via Dataflow engines. In any case, Peter, thank you very much for agreeing to give a talk. I think this is going to be a very interesting thing, and I'm looking forward to hearing what you have to say. So I'm leave to you the problem of introducing yourself and your work. Thank you very much again.
Okay, welcome everyone. First of all, I'm very grateful for the invitation. My story is that I started to work with quantum computing 2 years ago when I got the opportunity to join the National Hungarian program of quantum information. Basically, we formed here a new research group, and the aim of this group was to bring together people coming from quite different field of expertise. And the collaboration with the Grok and Maxwell technologies are in line with this concept, because we could further extend our repertoire of very useful tools to solve computational problems. One of our projects benefiting from this collaboration is about quantum gate decomposition, meaning that the central question here is to how to compile quantum programs in terms of elementary operations that can be executed on real quantum hardware. Okay. Ideally, a time evolution of quantum mechanical systems can be described by unitary matrices, because these are the operations that preserve the norm of the quantum mechanical state. And these unitary operations can describe either the whole quantum program or the elementary gate operations or whatever. Okay, I am assuming you know that all of such quantum logical gates are transforming the state of the qubit registers, and each qubit is an elementary unit of quantum information. Here you can have, instead of two distinct values of 0 and 1, you can have a superposition of state 0 and 1. And according to quantum mechanics, we can visualize the state of the quantum qubit as a three-dimensional unit vector pointing at some position on a sphere. This is called block sphere, and each physical transformation on a qubit can be mapped as a rotation of this three-dimensional vector over the block sphere. These single qubit rotation are labeled by these purple boxes over the timelines of the qubits. Another class of quantum logical gates are the ones which are applied on more qubits at once. For example, here you can see so-called CNOT gate, which depending on a state of one qubit makes or makes no transformation on another qubit. So this transformation also has an analogy in classical information technology, but in quantum mechanics it has a much deeper meaning. In particular, we can introduce entanglement between qubits using such multi-qubit gates. The entanglement is a very particular thing in quantum mechanics. Basically, it's an invisible wire between two qubits or particles, meaning that the state of one particle has a direct effect on the state of the other particle without having any wires or any other physical interaction between them. You may probably heard about the Nobel Prize this year, which was given to three physicists demonstrating this kind of quantum mechanical nature between photons. Okay, so this is a very fundamental resource to do quantum computing together with the superposition state of the qubits. It is also important to notice at this point that the single qubit logical gates together with these two qubit CNOT gates form a so-called universal gate set, meaning that any quantum program can be expressed as a sequence of these logical operations. Okay, mathematically, the problem is to expand a quantum mechanical program labeled by U in terms of a product of many other unitaries, like here in this expression. But you know, this is inevitable to run any program on quantum hardware, so we need some kind of a solution for this, even if it is a hard problem. And there have been developed many strategies to solve this problem. Some of them are follow a deterministic algorithm, like the one applied in universal Q compiler incorporated into the Qiskit or TCAT coming from Cambridge. This solution follows some complicated theorems and rules coming from linear algebra. The problem with this solution is that they produce quantum circuits with too much gate operations. You know, these days we have noisy quantum processors, and by accumulating the error over many quantum gate operations, at the end you won't get any reasonable outcome from the processor. So you need somehow to compress this circuit to contain fewer operations, and that's the way how you can get some reasonable outputs from quantum processors. Another class of quantum compilers are about to solve this problem. They basically are reformulating the synthesis process of the compilation into an optimization problem. So they are trying to approximate a quantum program labeled by U in the previous slide by a quantum circuit. And by optimizing the parameters of the circuit, they are trying to get closer and closer to the original quantum program U. To this end, we need to come up with a way how to quantitatively compare the quantum program we are about to compile with the circuit. We need to come up with some metric to quantify the distance between these two quantities. And this can be done following a very simple physical idea. Let's say this U is the original quantum program we are about to run on the processor, and the V is the unitary that we extract from the trial quantum circuit that we are using to approximate the quantum program U. if these two unitaries are equivalent to each other, then by applying them as a time evolution to a physical state, we are expecting to get equivalent physical state, meaning that the inner product of this state would be unity, you know. And if we take an average of this inner product over the whole Hilbert space of the quantum mechanical state, we should get unity as well if these two unitaries are equal to each other. If they differ from each other, then this integral would differ from unity. It would be less than unity. So this integral is called fidelity. It's a quantitative way how to characterize the difference between these two unitaries u and v. And after some math, it can be shown that this integral can be easily calculated with the cost function called Hilbert-Schmidt test, which is basically a trace of the product of these two matrices. And the fidelity can be calculated using this simple formula. In exact decomposition, the fidelity is 1, as I just explained. And in this case, this function c reaches its minimum 0. Okay. So this Hilbert-Schmidt test can be the cost function in the optimization problem. If we find its minimum, then we can find the approximation of the quantum program U. There is an even simpler form for the cost function based on the Frobenius norm, which is the sum of the square of the matrix elements. So if we calculate this norm for the difference between the matrices V and U, we again get the trace of these two matrices, but this time only on a it is linearly involved in the expression, and we need only just the real part from it. And if we introduce a new formula for the fidelity based on this Frobenius norm, it can be shown that this fidelity is always less than the fidelity from the previous slide. So if we find a solution for the optimization problem using this cost function, it will be also a solution for the optimization problem with the cost function from the previous slide, which was physically, I think, much better justified. Okay, but having the cost function is not enough to solve the problem. We need to introduce a model to parameterize the quantum circuit, because you know the three parameters which are encoded in those rotation angles of the single qubit operations, for example, are encoded within this matrix V. There are many strategies how to come up with such models. I will describe some of them for you just to get a feeling about the variety of this field. For example, here is the strategy implemented in InQueue Search, developed by Berkeley National Laboratory. Here, the parameterization of the circuit is treated as it is, as a combinatorial problem. Basically, the quantum circuit can be breakdown down to 2 qubit building blocks made of 2 qubit gates, like a CNOT gate and 2 single qubit rotations. And you can you can start to build up your quantum circuit made of such 2 qubit building blocks. And here in this InQueue Search implementation, they try to solve the optimization problem at each node of this search tree. This way, they can get a very nice quantum circuit, very closely approximating the original quantum program, but the execution time of this algorithm scales very badly, of course. Another way, also developed by Berkeley National Laboratory, tries to break down the initial n-qubit unitary into the product of into a product of unitaries acting on some subsets of the qubit register. For example, acting only on the half of the qubits. This can be done by this general parameterization of unitary matrices. By limiting the parameter alpha, some components of this parameter vector to 0, you can exclude bases from this parameterization, and this way you can limit the action of the resulting unitary down to subsets of the initial qubit register. And this step can be iteratively repeated until having single or 2 qubit unitaries which can be analytically decomposed. Okay, this algorithm scales much better. Okay, the execution time of this algorithm scales much better than the previous one, but due to the general nature of this parameterization, the produced circuit is usually significantly deeper, containing more operations. Now, I would like to describe you the strategy developed in our group and implemented in the SQUANDER package, which is an acronym for Sequential Quantum Gate Decomposer. I won't go into detail about this acronym because it would take a long time. I will just briefly describe our algorithm. We are also building up our quantum circuit from 2 qubit building blocks, but instead having C0 operations, we are having parametric 2 qubit gates in this 2 qubit building block. This parametric okay, the nice thing about this parametric 2 qubit gate is that they can be represented by let's say a single parameter, and depending on the value of this parameter, this gate can be turned into a simple identity gate, in which case it can be simply excluded from the circuit. So the strategy is to put many of such 2 qubit building blocks into the quantum circuit, try to solve the optimization problem, and then exclude from the circuit as much of these 2 qubit building block as much it is possible, using, for example, this identity of turning some of them into an identity gate.
What gates are U3 here?
U3 are single qubit rotation. Okay, these are rotating the unit vector along the block sphere. Okay, usually they have three parameters because you can parameterize the rotation in three-dimensional space with three parameters.
So they're also parametric.
Yes, of course.
Okay.
Okay, these single qubit parameters are parametric. Yes. Okay, we use this strategy in our decomposing or quantum compiler tool, and of course we made a comparison between these strategies. For example, we try to decompose quantum programs available in an online database, which was published as a part of Qiskit Developer Challenge several years ago, or we can also do the comparison on some well-known algorithms like InQueue Search or quantum Fourier transformation and so on. Our benchmark results are summarized in this table. Basically, we are showing the gate count of the C0 operations. You know, in experimental setups, the realization of these 2-qubit gates are much harder than the realization of single qubit gates. So that's the reason why it is a common practice to characterize the complexity of the quantum circuit with the count of these 2-qubit gates. And if you compare our results, you would see that SQUANDER, this is our tool, generated quantum circuit having systematically less of these C0 gates than the other two optimization-based algorithms. Only one example is here for which our tool produced higher C0 gate count, but this is a very special 3-qubit program having very few gates in it. Comparing with other or continue the benchmark using other examples, our SQUANDER tool still shows a better performance than the other ones. It is also interesting to compare the results of these optimization-based algorithms with deterministic ones, for example, implemented in the Qiskit package. You see that there is a real difference between the C0 gate count. Qiskit produced a quantum circuit having C0 gates almost 10 times more in the quantum circuits. So it's a huge difference. The problem is that Qiskit can do this decomposition within several seconds, but the time scale of optimization-based quantum compilers, it's much higher. So this is the problem with the optimization-based compilers. We also can compare the C0 gate count with the initial C0 gate count. You know, all of these example quantum programs are given in form of quantum circuit in that online database I just mentioned 2 slides ago. And you can see that in many cases, SQUANDER could give a better decomposition than it was originally given in the database, which is also a very nice thing. And the fidelity of all of these circuits produced by SQUANDER or QFast or InQueue Search are very, very close to unity. So maybe they are even in exact decompositions. We don't know for sure, but we just can tell that they are very close to the exact decomposition. And due to the high or long execution time, there is another issue related to the optimization-based compilers, namely that all of these examples are at most 5-qubit programs. So there are no more qubit than 5 in these quantum programs. And the reason is that the evaluation of the cost function during the optimization procedure is very expensive. Okay, basically you need to evaluate the unitary V associated with the trial quantum circuit, or more efficient is to apply the quantum circuit directly on unitary U dagger, and this way you will get the product of these two unitaries. The problem is that the unitary U is in general a dense matrix, and you need to transform all of its elements, making the number of operations to be 4 on the power of n, where n is the number of qubits. You know the size of these matrices is 2 on the n times 2 on the n, and having m quantum gates in the circuit, you need to repeat this procedure m times, so it increases linearly the complexity of the evaluation of this cost function, and you also need to evaluate its gradients, because you know you are doing some kind of a gradient descent optimization algorithm to find the minimum for the cost function, and for that you need to evaluate the gradients. So to scale up optimization-based quantum compilers for higher problems containing more qubits, you need to somehow increase the performance, the computational performance of this cost function, and that's the point where Grok or Maxer technologies comes into the play. Basically, to do this job, we used an FPGA based accelerator. The reason behind choosing FPGA and not GPU, maybe I will explain later. Now I would like to tell you more about these FPGA things. So you may know that on an FPGA chip you have many programmable hardware units, which okay, you can program these hardware units, but you cannot change their program during execution time, and that's a big issue with FPGAs, because you have a finite amount of resources given on the chip. And for example, if you would like to increase computational concurrency, you will need to implement more of these resources. If you would like to increase the number of supported qubits, you also need to increase the usage of resources in this direction. Or if you would like to increase the computational accuracy, you also need to give more resources for this. And since you have a finite amount of resources, you need to come up with some kind of a reasonable trade-off between these three dimensions. On top of that, you need to come up with an implementation on the FPGA chip that can support an arbitrary quantum circuit made of single qubit rotations and conditional 2-qubit gates. I just showed you some slides before, because this is what is involved in our quantum compiling process. And you need this functionality without the reprogramming or recompiling the FPGA, because this takes much time. Okay, so basically you need to have a full-fledged universal quantum computer simulator implemented on the FPGA chip to solve or to increase the computational speed. And of course, doing this work in a raw VHDL programming, it's very troublesome. And the solution for this problem was given by the high-level development framework of Maxelar Technologies. Basically, we are speaking about a Java-based development framework that is designed to translate higher-level objects into low-level VHDL components, which can then be processed with to place and route on the FPGA chip by the low-level tools of the hardware vendors. This high-level development framework coming from Maxelar, the realization of a so-called Dataflow programming model. If some of you are not that much familiar with this concept, it is very easy to understand. You just need to think about a long production line, for example, carrying some cars over the line, and at each point you have machines to do some work on the cars. And if the production line is well pipelined, so you have many cars over the line, then you can say that each machine can do his job, and you can reach a high level of concurrency. Okay, the same can be imagined by flowing some streams of data through the FPGA chip, and having the components on the FPGA chip to get some transformation on the data elements. If you are clever enough, you can retrieve the cost function at the end from the FPGA chip. Okay, and the Dataflow engine can be understood as a combination of the FPGA hardware itself and this Dataflow programming model. Okay, so this is the way how we try to implement our universal quantum computer simulator on the FPGA chip. But to this end, we need to think about quantum gate operations in the context of Dataflow programming. Okay, here is a sketch that might help you to understand the main ideas. Let's say we have a unitary V. The quantum gate operations can be break down onto operations on the individual columns of the unitary V, because each column can be considered as a quantum mechanical state, and the elements of the columns are basically the amplitudes, complex amplitudes of the superposition made of the basis vectors corresponding to the state, to the product state of the quantum qubits. For example, the first basis, in the first basis vectors, all the qubits can be, for example, in state 0. In the next basis state, we have one qubit in state 1 and the other two in state 0, and so on. So we can label all of the basis vectors according to the individual state of the qubits. If now we have a quantum gate that operates on the second qubit, if we start the labeling from 0, then the qubit labeled by red is the second qubit. So if we have a gate operation acting only on the second qubit, then the other two qubits, and in this example, need to be unchanged. You know, so the quantum operation mixes only amplitudes that that differs only in the bit associated with the qubit on which the gate operation is applied. Okay, and this way we are combining, the quantum gate operation is combining each time pairs of such amplitudes which are labeled by these colored lines, and the output of this gate operation replaces the transformed amplitudes at the same position. So the gate operation has two inputs and two outputs, and since it's a linear transformation, it can be represented by a 2x2 matrix. And now, having the columns of the unitary V flowing through this gate operation, while it select and combine some of the amplitudes, we can rely the Dataflow model of the gate operation. Of course, there is much more details that need to be put in place. Here is the scheme of our quantum gate implementation of the FPGA chip. First of all, you need a component producing data related to the gate operation. You need to tell the gate on which qubit it should operate. This is called a target qubit. You also need to give the label of the control qubit in case you are simulating a 2-qubit controlled gate, and this component also needs to generate that 2x2 unitary matrix of the transformation we have discussed a slide ago. Okay, another component is responsible for the iterations over the bases. And for each base, it needs to determine its pair on which the transformation is applied. Basically, we need to just flip the bit on the position of the target qubit. Okay, this can be done easily. So having the indexes of the amplitude pairs, we need to select these elements from the stream of unitary V. To this end, we multiplex this stream into two arms, and on one of the arms we apply a stream offset. The offset parameter here is basically the difference between these two indices. In this specific example, having the gate acting on qubit number 3, this is, for example, 48 minus 89 minus 81. Okay, and on the other arm of this data stream, we need to we need to counterweight the latency associated with stream offset. You can't just pick some elements from the thin air. You need to fill on-chip memory with elements coming from unitary V, and this needs several cycles from the execution. And to counterweight this latency, we need to put a stream FIFO on the other arm. And this is a very important point of the design, because it tells you that that this design of the gate operation is memory intensive. You need to implement much of the on-chip memory resources, and the amount of this memory is also a limiting factor of how many gate operations you can get implemented on the chip. The final component is the unitary transformation itself. Okay, you need to stream here the 2x2 unitary matrix of the transformation. You also need to know the states of the control qubit, because you need to decide whether apply or not the transformation in the case of 2 qubit gates. And also you need to know the state of the target qubit to know whether you are calculating the upper or the bottom one of the amplitude pairs. Okay, basically this unitary transformation is a linear combination of the amplitudes with complex values. So we are having here 2 complex multiplications and 1 complex addition. Okay, to do multiplication with numbers on the FPGA chip, you have you can utilize the so-called digital signal processing units, which have 18 and 27-bit input ports to calculate the multiplication of 2 signed integers. Okay, I don't want to go into details, but according to our tests, having 32-bit fixed point representations for the amplitude and for the transformation unitary is sufficient to get good results. And the job here is to tile these 32-bit multiplications over multiple DSP units as efficient as you can do. Okay, to this end, we need to split these 32-bit numbers into bit chunks. We use, of course, 16-bit chunks labeled by A dot, A1, B dot, and B1. And if we would like to multiply numbers, these are real numbers, A and B, we are ending up with the following expression. Here we need to calculate A1 times B1 and A naught times B naught. Both of these multiplication takes 1 DSP unit to calculate, but the expression in the middle can be reformulated. Instead of having 2 multiplication, having only a single multiplication and another additions by reusing these previously calculated products with A1, B1, and A naught, B naught. Another detail is that accounting for possible overflow, here we need to do 17 times 17 bit multiplication, but it still fits into the input ports of the DSP unit, so we are fine. So eventually we can do this multiplication with 3 DSP units and 5 additions. For the additions, we can use lookup tables and flip-flops to do the adequate pipelining during the calculation and so on. But we have plenty of those resources. To sum up the resource requirements of this linear transformation in overall, we are ending up with 18 DSP units needed for a single gate operation, and also some lookup tables and flip-flops. Now the question is, how many of these gate operations we can place over the chip, because you know the limiting factors are the DSP units and the available memory on the chip. The design is that if we place multiple gate units on the chip, then we can chain up them into a circle. Okay, here is missing one purple arrow. I don't know why, but it doesn't matter. Basically, we connect the output of one gate operation to the input of the other one. You know, this is a production line. Okay, and you can have flow the unitary V over this circle, and each gate is operating on some of the elements of the unitary V. If we have a quantum circuit with a larger number of gates than we have implemented on the chip, for this case, we are buffering the unitary V in the onboard memory of the FPGA card. Okay, so this is not the on-chip, but the onboard memory. It's much larger usually. And then, of course, we can have another turn, another circle of the unitary V along these quantum gates. Okay, you know, each quantum gate operation takes quite much cycles from the execution, because we need to process each element from the unitary. So each gate operation takes 4 on the power of n clock cycles to accomplish one gate operation. And you need to refresh the gate operation with new gate data only after finishing one gate operation. So this is done just occasionally. Hope you understand my point. So there is enough having only one component on the chip supplying the gates with metadata associated with the gate operations. We also get having it run on smaller frequencies to lift some of the timing constraints on longer data paths, because it's sufficient to supply gates with the necessary data this way. We also need to design some components to manipulate with the onboard memory to generate the correct memory addresses for the elements of the unitary V. And of course, you know, we are not calculating on only the cost function, but also its gradient, which okay, to calculate the gradient for a cost function, we need to only replace one of the gate operations with its derivate function. Okay, so nothing else is changed, just we need to supply the given gate with a little bit different data, but we can calculate not just the cost function, but also the gradients with the same design. And to do that, we need to come up with a good strategy to stream these data associated with the gradients between the chip itself and the onboard memory. So this is quite a complicated thing, but it can be accomplished. At the end, this is the scheme representing the resource usage on one of the superlogic regions of our FPGA chip. We are using this Xilinx Alveo U250 FPGA chip, which is made of 4 of such SLR regions, having just weak wiring between these SLR units. So it wouldn't be a good strategy to go for high data throughput between these regions. Instead, we implemented 4 independent quantum computer simulators on each of these regions, because we can split the calculation of gradients between these regions, so it makes sense. And at the end, on each of these superlogic regions, we could place 108 gates operating in parallel. It's a little bit detailed that we have organized them in 6 blocks, where the gates in a single block operates synchronously, driven by a synchronous clock-enabled signal, while the different blocks can operate asynchronously, having some FIFOs to buffer some data between them if it's necessary. In total, we had more than 400 gate operations on the whole FPGA chip working in parallel, and we also can calculate the execution time to calculate the cost function and its gradients, because we know in each clock cycle what happens on the FPGA chip. Okay, this is given by this simple formula. We need to calculate gradients for each of the 3 parameters in the model, plus the cost function. Okay, on each FPGA card, we can split the workload over the 4 SLR regions. We need to do 4 on the power of n cycles for 1 gate operations, and we need to multiply this execution time with the number of round trips that we need that the unitary we need to absolve to get the effect of all the gates in the quantum circuit. Okay, we also can calculate the number of operations performed over a second, and this model gave us about 2.7 tera operations per second. So I think it's quite a decent performance on the chip. And if we compared this performance with the CPU, we end up with a 6 or 13 times speed up compared to a 32-core AMD processor. We had smaller speed up with problems including fewer qubits and higher speed up with more qubits. We also could distribute the calculations over multiple FPGAs. Okay, you know, because we need to distribute the calculation of the gradient components, which completely fits into the concept of parallel 4 algorithm, so it can be easily distributed between different FPGAs. For this, we use 2 CPU servers, each of them having 3 FPGA cards, and the CPU servers were connected with a simple network, and we measured about 30 kilobyte per second data transmission during the execution. And you know, with this setup, we realized the speed up to 78, which is a nice thing because it enabled us to scale up the quantum decomposition up to 9 qubits. Here we compared our result only to Qiskit because the other 2 optimization-based tools were out of the game. And you can see the difference in the number of C NOT gates. Okay, here CX labels the number of C NOT gates, and D labels the depth of the circuit, which is practically the longest sequence of gate operations along the circuit. In average, we have achieved gate compression more than 95% on average compared to Qiskit, and we also made improvements over the gate counts on the online database. So we could improve those circuits. Okay, still having a very good fidelity in the composition. Now the question is, how can we further improve these capabilities? Because the problem is still that we can't go any further than 9 qubits, and it's still too few, you know. And there are several ways in our mind how to improve this story. First of all, okay, I will explain it on the next slide, but the thing is that the main problem is to construct the initial gate structure and solve the optimization problem for it. It might take even a week for a 9 qubit problem. But then if we start to compress the quantum circuit, okay, we can do, for example, randomly select some of those parametric 2-qubit building blocks, exclude it from the circuit, and try to solve the optimization process once again. Okay, this is depicted here on these figures, and our observation is that even if we need to solve a very similar optimization problem than to construct the initial gate structure, we can solve the optimization problem in the iterations of the compression in half an hour, if it can be solved. Okay, and this is a huge difference compared to 1 week. And basically, we need to solve the same optimization problem. The question is, what is the difference? What makes this huge difference? The other point, which is in our mind to as a further or future project is to scale up the compilation process up to even more qubits. Of course, we don't want to scale up the optimization process itself, but rather we might aim to reorganize the quantum circuits and come up with smaller groups of quantum operations that can be optimized within a larger quantum circuit. Okay, so this is a project for the future, but the first point is even more interesting. Okay, so what makes the difference between in the efficiency to solve this optimization problem, and the difference is in the initial parameter set that we give to the optimizer to begin with. Okay, in the compression iterations, we are simply reuse the parameter set obtained during the process of constructing the initial quantum circuit, and just exclude some of the parameters that are corresponding to the building blocks we have just randomly select to exclude from the circuit. And our observation is that we can solve the new optimization problem without this building block much easier than constructing the initial circuit. Okay, we don't have a well-defined or well-formulated answer for this question. Probably in the it can be explained by some hidden structure, hidden correlations between the qubits, which are encoded by these parameters. Okay, I don't expect that we would be able to solve this problem, because if we could solve the whole quantum gate compilation problem, but maybe we can use machine learning to predict those hidden correlations between the qubit that makes the solution for the optimization problem much easier to find. Okay, since we can extract the unitary from the quantum circuit very easily, we can prepare many data for machine learning, and our idea is to use machine learning trained on these data sets to predict parameters for the construction of the initial parameter set. Okay, but we are also very excited to use these cards, which we received some months ago from Grok, to use in some other kind of calculations, which is different from the one they were initially designed for. For example, we can ask whether we can use Grok chips, Grok cards, to do quantum computer simulation, for example. And the answer is that we have a design for that, but first I need to describe some basic concept about the Grok chip for you. I don't want to go into much details. You can find it in a publication released 2 years ago by Grok. I just want to mention some basic ideas. Okay, the Grok chip is built of several kind of functional slices. For example, you have on-chip memory of 110 megabytes on each side. You have also some functional slices to make permutations and or other element shifting like operations on the tensors. flowing through the Groq chip. There are also some slices to calculate matrix or tensor products, and in the middle you have units to do element-wise arithmetic transformation on the tensors flowing through the chip. In each direction, you have you can utilize 32 streams to which can carry your data. Each stream can carry 1 byte element, but in a okay, they have 320 times parallelism. Okay, they are made of 320 lanes, and over these lanes you can carry 1 byte element data streams. Okay, each of the computational slices can perform some kind of operations on operands described here at the bottom of the slide. So basically you can have operands as integer 8 up to integer 32, or float 16 and float 32, but the matrix multiplication works only on signed multiplication of integer 8 and float 16, but you do the accumulation of matrix multiplication, the result should be wider, okay, to handle possible overflow. So the matrix multiplication results in 32 and float 32. Okay, we have come up with a very simple design to use Groq chip to do quantum computer simulation. Okay, first of all, remember the gate transformation I described you some slides ago. Remember, we need to combine pairs of amplitudes, and since we are pairing the same amplitude, the same amplitudes from each column, we can use the vectorization capability of the Groq chip to fetch the whole row and do the gate operation on the whole row, on the pairs of whole rows at once, using this 320-way vectorization. Okay, so we need to fetch complete rows from the stored unitaries in the memory, but since we have only one read port on each memory slice, we need to keep 2 copies of these unitary matrices in the memory and stream the rows from each of them. And also we need the data associated with the gate operation. Having complex transformation, and we have seen that 32-bit floating point operations are sufficient to get reasonable results for our quantum gate compilation process. We can think about how much streams we need to carry these data, and it turns out that to carry all of these data, we need 24 streams from the available 32 ones. So it seems to be viable. Also, if we think about the arithmetic operations of combining these streams, here it is at the top of the slide. You see we have 2 complex multiplications and 1 complex additions. In total, we will need 14 of the arithmetic logical units capable of doing these arithmetic operations, and in total we have 16 of these units on the chip. So this also seems to be viable, and since the Groq chip is a deterministic hardware, we can also calculate its performance in advance. okay, before we have implemented it. And it turns out that even excluding the matrix multiplication slices from the picture, because we have sparse gate operations, so we can't use those elements, which are, by the way, the most powerful elements on the Groq chip. Still, we are getting, or we are expecting to get 50% more performance from the Groq chip than we are getting now from the FPGA. And due to the larger memory, we also expecting to be able to a little bit scale up the number of the qubits in the decomposition. Okay, we also thinking about another use cases for the Groq chip in quantum simulation processes. In most of these applications, the 32-bit arithmetical operations are not sufficient. We need to do double or long double arithmetics. The question is how we can do it on the Groq chip, supporting natively only 32-bit operands. And we have designed a solution for that. Basically, as a first step, we can convert an array containing of double and long double values into an array of integer 64 values. And also we need an exponent. Okay, we can convert a double value into an integer value plus an exponent, but here we define the exponent and node globally for the whole array, not for its elements, but the whole array. Okay, then we can split this int 64 value array into 7 plus 1 sign bit chunks. Okay, it can be easily done using this expression. And using these chunks, we can do, for example, matrix multiplication directly on the Groq chip. I don't want to go into details, but let's say that we need to calculate this sandwich product with two vectors on the sides and the matrix in the middle exponentially many times to simulate some photonic quantum computing processes. Okay, let's take a look, for example, to the product of this vector times matrix using those bit chunks introduced in the previous slide. This product can be expressed using this formula. Here in the formula, we need to calculate each pair of the chunk multiplications. To do that, we can arrange the chunks of these arrays into this bigger form, and we can calculate all of these pairs in a single shot this way. And also we can extend this procedure to complex arithmetics as well, organizing the values, the real and the imaginary parts of the values in this blocked form. So it's very straightforward. Of course, the matrix multiplication units produces 32-bit integer results. So to be able to use the results in further calculations, we need to somehow transform these 32-bit results back into 8-bit chunks. Okay, we need to do bit shifting, accumulating and so on. So it's a pretty complicated thing, but it can be implemented on the Groq chip. And at the end, in our experiment, we could realize a numerical accuracy up to 10 on the minus 15 in these double and long double arithmetic operations compared to the CPU oracle. Also, since we need to process generally smaller matrices, not bigger than 80 times 80, we could fit more of these multiplications onto the Groq chip at once. We managed to put 8 of such multiplications at once on the chip, and according to our experiment, we realized for these operations 32 times faster performance than doing it with the NumPy and EQUID with BLAST behind it and so on. Okay, you know, the parallelism on the CPU in this case is governed by the BLAST working behind NumPy, and according to our experiments, only 20 threads were utilized to the calculation. So we are still working on this project. We are mainly focusing now to reduce the I/O times, to transferring data between the Groq chip and the host CPU itself. And then, okay, I also prepared you a little demo regarding the Groq chip, and basically it's the end of my presentation. I am just concluding our work. So we managed to develop a universal quantum computer simulator on an FPGA chip, and it helped us to scale up the quantum gate synthesis up to 9 qubits, and we also have in mind many improvements for it. Okay, here I summarize those grants that supported our work. If you have any questions regarding our work, you can contact us or me through this email. And I will like to finish my presentation with that demo I just mentioned. So I'm just switching the screen, and this will be very interesting. So this is the implementation. Hope you see it. This is the implementation of that double or long double precision multiplication on the Groq chip. Okay, Groq provides you a very intuitive tools to how to say, to make your implementations more optimal to solve some streaming conflicts and so on. Here you can see the data transfer during our multiplication implementation. First, we are streaming the matrices towards the matrix multiplication slices. Okay, these are those integer 8 chunks. We are doing 8 multiplications at once, so that's why we are utilizing both hemispheres, both sides of the chip and so on. And here in the middle, you can see how we are recombining the resulting 32 bit results coming from the MXM slices back into integer 8 chunks to be reused in further chained operations. Okay, basically these reorganizing into 8-bit chunks take even more times, more cycles than the multiplication itself. In total, we are doing the multiplication in around 1,200 cycles. Okay, this is our limit, and then we basically do other chaining operations here. One of our well-gifted PhD student, Gregory Morse, developed the gray code. Okay, so to do further calculations, we need to produce additional computational data, and we are doing it directly on the chip to exclude or to reduce the communication through the PCI slot. And this is done by transferring some rows and columns of the input matrix in gray code ordering. So to this end, Gregory implemented this gray code counter and gray code style updating of the matrix, and this is what you are seeing now. Basically, we are transforming 1-byte chunks of the matrices. Okay, so I think my time it's finished, and I also came at the end of my talk. So I am very grateful. Again, I'm very grateful for the opportunity to present our results here at this colloquium. And if you have any questions, don't hesitate to ask us. Okay, thank you for your attention.
Yeah, that's better. Are there any questions?
I see something in the chat.
Okay, chat, I see the chat. What's the performance running on GPU? Okay, we are not, okay, we don't have the implementation for a GPU. That's a good question anyway. We don't have that comparison. Our goal was to scale up the capability to generate quantum circuit, to compile quantum programs into quantum circuits, and this is I think the main message of our work. To use DFE as an accelerator for this is only a tool. Okay, so we didn't have in our focus to compare its performance to other type of accelerators. We just wanted to decompose larger and larger unitaries. But you know, the reason why we like Dataflow engines or FPGAs is the way we can utilize concurrency or parallelism on these devices. Because, you know, if you would like to use GPU, for example, to make parallel the gate operations, it's not that easy, because, you know, as I told you, you need to transform pairs of the amplitudes, and these pairs might be distant from each other. And if you start to do parallel execution of gate operations, even if they commute with each other, they can overlap with each other, and eventually they can interfere with each other. So it's not an easy task to ensure the correctness of the calculations. Okay, and if you would like to keep up such a parallel calculation, you will need to pay some penalty, some performance penalty to ensure the correctness. And that's why we like FPGAs, because of this data flow programming model. We don't need to pay any performance penalty. Okay, so maybe there might be some GPU implementation that might run even faster than our DFE implementation, but I am not that sure about it. Because it's not that easy to make the simulation of quantum circuits parallel. It's not that trivial.
Anyone else? Well, thank you very much, Peter, for your presentation. And I see this this will all get out onto the web, and we'll pick up more questions and so forth. And I assume that you'll be available to
Yes,
answer questions and so forth if that's the case. And
so yes, I hope you enjoyed a bit the talk. Maybe it was a bit too much at the end, but okay, I hope you enjoyed it.
yeah, thank you. Thank you all.